Today we start section 5.2 where we look at binomial probabilities, and we'll look at the binomial distribution, which is a discrete distribution. Remember in section 5.1 we talked about probability distributions. We mentioned there were discrete ones and continuous ones, and this is a discrete distribution that we'll be looking at. So to get started here, basically a binomial experiment is a statistical experiment that has exactly two possible outcomes for each trial of interest. So two outcomes, so it's bi meaning two, and sometimes these are called, instead of binomial experiments, sometimes these are called Bernoulli trials. So I'll write this down too. And this is named after Jacob Bernoulli, who was a mathematician who studied these in the late 1600s. So to get started, let's look at these features of a binomial experiment. So remember, it's binomial. It's basically an experiment with exactly two possible outcomes. So there's going to be a fixed number of trials denoted by the letter n. So a perfect example of a binomial experiment is a coin flip. If you flip a coin, you could have it land heads or tails, two outcomes. So in this case, let's say we're going to flip a coin 10 times, so then n would be 10. So there'll be a fixed number of trials. These n trials are independent and repeated under identical conditions, so they're independent from one another, right? So if I flip a coin and then flip another coin, that first coin flip has nothing to do with the outcome of the second coin flip, right? So they're independent, like we talked about in chapter 4. Like rain in Topeka has nothing to do with whether you eat lunch tomorrow. It's just independent, right? So the trials are going to be independent. Each trial is only two outcomes, success and failure. So this is where we have to divorce the meaning of these words a little bit. So success and failure. Success in this context doesn't mean something like necessarily a good thing. It just means you found what you were looking for. So maybe you're going to flip a coin 10 times and count the number of heads. So you would count the number, every time it lands heads, that would be a success. And when it lands tails, it's a failure, right? So it doesn't mean like, oh, I failed, I'm sad. It's not like that at all. It could be like, oh, success, we found brain cancer, right? So it doesn't mean, don't think of this as success meaning it's a good thing and failure a bad thing. It just means success means the thing that we were looking for, we found it. If we're flipping a coin and counting the number of heads, every time it lands heads, that's a success. Every time it lands tails, that's a failure, right? So just think of it that way. For each individual trial, the probability of success is the same. We denote the probability of success by P. So the probability of success is going to be P. Probability of failure is Q. Now, since each trial results in either success or failure, then we know that P plus Q has to be 1, right? Because remember, in this experiment, there's only two outcomes. So if we add the probabilities of each of those outcomes, it has to be 1. So the probability of success plus the probability of failure, those are the only two things that can happen, right? Equals 1. And if P plus Q equals 1, then we can easily see that Q equals 1 minus P, right? If P plus Q equals 1, and you want to get Q by itself, you would subtract P from each side and get Q equals 1 minus P. So a lot of times you'll be given P. You'd be given the probability of success, and you won't be given Q, but you pretty much know what it is because P plus Q have to add to 1, right? There's only two outcomes here for a Bernoulli trial or a binomial experiment. There's only two outcomes. So the probability of success is P, the probability of failure is Q, so they have to add up to 1. And the central problem of a binomial experiment is to find the probability of R successes out of n trials. So like, let's say there's a basketball player who makes, uh, let's say this person makes 86%. Let's say it's a GRCC women's basketball player. Let's say she makes 86% of her free throws, and she's going to go to the line 11 times, and you want to know what's the probability she makes 7 or more of those shots. That's where we would be able to figure this out with using the techniques we're going to learn when we study binomial experiments. So to calculate these probabilities, there are 3 approaches we can take, but we're really just going to take one. So there's the binomial formula, which I'll explain for the first couple of these, just so you'll see how it works. Although we're really going to just use the calculator, which will then calculate this for us. But you can see in here, this is a combination of n things taken r at a time, and then p, probability of success, raised to the r power, times q, probability of failure, raised to the n minus r power. And that is basically what the calculator will do here. So we could use a binomial formula, or we could use a table. There's a table in the back of the book, table 3, which gives a lot of these answers. Of course, with a table, you're limited. The table is only so large, even though this is a pretty good sized table. The probability of success, if it's a table, it's going to go probably by 5. So maybe 5% or 10% or 15%, like that, where if we use the formula, we can plug in exactly what we want, and we can do that here too. So we'll look at a little bit with this one. I'm not going to do anything with a table. We'll just tell you it's in the back of the book. I may talk about it a little bit, but not much. Mainly, we're going to concentrate on this. This is pretty much what everybody does nowadays, is this third one here. So let me just point out a couple things here. So this is the probability of r successes, right? We're going to find the probability of r successes out of n trials. Make a quick note of that. R successes and trials. So this is the probability of R successes. So the commands that we'll use a lot in chapter 5 is binomial PDF and binomial CDF. So when we talked about probability distributions in 5.1, we said we could have a probability distribution table, right? We could have a table as long as we have a discrete distribution. And then we looked at a table, then we changed that, took that table and made it into a graph. And then this is just a probability distribution function. So here's what this stands for: binomial PDF, probability distribution function. And then this one is a binomial CDF. Well, really it's a cumulative probability distribution function. So it'll make sense when we look at this, and then this is just a cumulative distribution. So the things we need to know: NPR, the inputs are the same for both commands. NPR, just think of NPR radio, makes it easier to remember NPR. So what we have to know is that N is the number of trials. So number of coin flips or something like that. P is the probability of success. Now, since P is the probability of success, being a probability, what does it have to be? Probability means P has to be between 0 and 1, right? Probability of success. So if that's not between 0 and 1, you're going to get an error. And then R is the number of successes. NPR, it's the same for the binomial CDF. So, all right. So let's let's get going on these, and I'll show you how this works. It'll make more sense if we do some examples, and I can show you exactly how the command works. So let's look at this example. So we have got, let's see, 3% of all DVD players manufactured by a large electronics company are defective. A quality control inspector randomly selects 5 DVD players from the production. So 5 DVD players. So think of it like this. Think of it as this huge pile of DVD players. Just think of thousands of them in here. Thousands of them are in here. Some of them are bad. 3% are bad. So when it comes to finding values of N, P, and Q, well, P and Q really are like they're interchangeable. Like you could pick P to be 3% or Q to be 3% in this case, and then you would just have to reverse them. And I mean, if P is 3%, then Q would be 97%. Or if you let Q be 3%, then P is 97%. So it's kind of arbitrary, but what I'll always do is I'll count success as the thing we're looking for, even if we're looking for it to avoid it. So when we say that 3% of these are bad, 3% of all DVD players manufactured by this company are bad, and this quality control inspector is going to select 5 of these, then what I'm going to do is I'm going to say, well, first, N is 5, right? We can agree N is 5. This inspector is going to select 5 of these. So P, I'm going to say P equals 0.03. Basically, what I'm saying is there's a 3% chance, if this inspector picks one of these, there's a 3% chance it's going to be a bad one because 3% of these are bad. And then if P is 0.03, Q has to be 0.97. Now what I was talking about before is that some people will reverse these, and that's okay, it doesn't matter. As long as we're consistent all the way through, we're going to get the same answers. But I'm always going to think of it like this. The thing that we're wondering about, like, none of them are defective, exactly one of them is defective. These are the things we're looking for, right? So I'm going to count those things as the success. If we find one, I'm going to call that success. So if 3% of them are bad, I'm going to say P equals 0.03. So when it says what is the probability that none of the DVD players are defective, none means that we are picking no bad ones. So R equals 0, right? R is a number of successes. R is a number of successes, so R equals 0. So if we were going to use that formula that I mentioned, we would say the probability, we'd write it like this: probability that R equals 0 equals, I'm using that formula above on this handout. So it would be a combination of N items taken R at a time, and then P, which is 0.03, would be raised to the 0 power. Then Q, which is 0.97, would be raised to the N minus R, which would be 5 minus 0, which would be to the 5 power. So one thing about using this, whenever you use this formula, these two right here will always add up to the number of trials. They always add up to, in this case, 5. And then you can look at this and see that the combination of 5 items taken 0 at a time, or remember the way our calculator does it, it would put 5C0, right? That's how our calculator does it. But either way you go, there's any combination of items taken 0 at a time is always going to be 1. So this is going to be 1. We know anything raised to the 0 power is 1, so this is also 1. So basically this answer is just going to be 0.97 raised to the 5th power. And if you type just that in, or if you type this whole thing in your calculator, we're going to get this number. We're going to get 0.8587340,257. Okay, so that's probably not the way you'll do it. This is most likely the way that you'll do it. The probability that r equals 0 equals, and what we'll do is use binomial PDF. And we put NPR, N, which is 5, P, 0.03, R, which is 0, right? NPR. R is the number of successes. We're saying none. None of these. None of the players are defective. That means none means R equals 0. Number of successes is 0. So to punch this in the calculator, just have you take a look at the video and we'll walk you through this. So if we want binomial PDF with NPR, N being 5, P being 0.03, and R being 0, we go to, see above this vars or variables key, there's the word that looks like distribution, or a shortcut for distribution. We're going to go there a lot from chapter 5 on. So we need to hit the second vars, and then we need to look for binomial PDF. You can scroll down or up to get there, but it's quicker to go up. And see, this is binomial CDF. We want binomial PDF, and then you hit enter. Okay, now some of you are not going to see this, so just hold on a second here, and I'll do this on a different calculator to see what you'll see. So with the newer software, it's asking you for the number of trials, so that's N. So I put 5 here. Probability of success P is 0.03. And then the only thing that's a little different is X value. Our book uses R, and probably about half of them use R. Half of the books use X for that, for the number of successes, and our calculator uses X. So it's asking for the number of successes, and for this we want 0. So for this version, you punch in your 5.030, then you go and paste it to the home screen, so you just hit enter. This comes up, and you get here. Now some of you have a different version, so with that, you'll get there in the same spot. You hit your second vars. I'll go down this time just so you can see this works too. We go to binomial PDF right here. Hit enter. And with this one, we just type it in 5. You need the comma. So it's N and then P.03, comma, and then 0. And you don't need to close it, but I'll just close parentheses and hit enter, and you get the same thing. You may notice that if you look at that, when you go to second vars and you see all those distributions, there are a ton of distributions that the TI-83 or 84 can handle, and we'll see a lot of them in this class. So what is the probability that exactly one of the DVD players is defective? Exactly 1, so R equals 1 this time. So again, I'll show you the, using the formula, show you how to do that, and I'll also show on the calculator. So using the formula, we're looking for the probability that R equals 1. So that is going to be a combination of 5 things taken one at a time, times P raised to the R, and then times Q raised to the N minus R. So again, these will always add up to 5. So if we punch this in the calculator, we end up with 0.13279399215. So roughly there's, if you look at what it's saying, it's saying there's about a 13% chance, right, of this happening. This is what we should have talked about before too. After we get an answer, we always want to make sure we look and say, does that seem reasonable? So Actually, I should have put this down also. This gets the same answer. So this is saying there's about an 86% chance that none of them are defective. So if we look back what we're working with here, 3% of these are bad. And this inspector is going to pick 5 of them. And with 3% being bad and this inspector picks 5, there's still about an 86% chance that none of them will be bad. Right? 86% chance. So what's the probability that exactly 1 will be bad? About a 13% chance that when this inspector picks 5 of these from this pile, it's about a 13% chance that exactly one will be bad, will be defective, right? So to do this same calculation, but on the calculator like we normally will, I'm going to mainly stress the binomial PDF version because that's what everybody does nowadays. Because it does the calculations for us. It's just quicker than us typing in numbers into the formula. So the probability that R equals 1, so this is going to be, we would use binomial PDF, right? NPR, so 5.03, and the only difference now is 1. And if you remember from before, if you have this in your calculator and you hit your second key and then enter, this will come up again. Then you can just change that 0 to a 1, right? That second enter cycles through the last commands. And if you do this, you should get the same number here. So in a normal class, when we don't take tests online, but when we're in class taking tests, and I'll say show work, this would be the part right here. This is your work, right? It used to be this in the battle days before we had graphing calculators. This would be the work we would show. So now this is the work we show. Instead of just putting this number here, this makes it clear that you understand how this command works and you understand what NP and R are and how they're used. So, okay. So then we've got the next part. What is the probability that exactly 2? So now we're probably going to get into a lower probability, right? Because think about what this is asking us. This is saying, in this situation right here, this person's going to pick 5 of these, 5 DVD players. Only 3% of them are bad, and this person's going to get 2 bad ones out of the 5. So that means somebody's kind of got bad luck, right? To get out of the 5 of them, have 2 of them bad, and there's only 3% chance of any being bad. So we know there's a 13% chance of 1 of them being bad. So to get another bad one in that pile is probably going to be kind of a low probability, but let's see how it works out. So this one, try on your own, make sure you try it, and then check back and let's see how you do. So let's do this 2 ways again. So I'll go probability that R equals 2. So that is going to be a combination of 5 items taken 2 at a time. Probability of success raised to the 2nd power. Probability of failure raised to the 3rd power. Another way you could think of it is there's 2 of these successes, right? Exactly 2, R equals 2, which means 3 of these failures. And if you do this on your calculator, you will get 214057. But I'm just showing that just, I guess, so you see where it comes from. This is really what I would expect you to do. The probability that R equals 2, because it says exactly 2. So R equals 2. The number of successes, 2, right? So that's going to be binomial PDF, NPR. And if you punch that in your calculator, you should get the same thing. So as a decimal, it's 0.008. So as a percent, it would be 0.8%, right? Less than 1%, right? Because you move this over as you want to. If you want to say it as a percentage, you move the decimal over twice, so you get 0.8%. So it's basically not very likely that you would get 2 defective DVD players out of the 5. But now we talk about something else. Now we're talking about what is the probability that less than 3. Less than 3, so they're not talking about a number. Before they said exactly 1, exactly 2, or none. This means less than 3. That means R could be 0, 1, or 2, right? Not 3 though, right? It says less than 3, not less than or equal to 3, just less than 3. So less than 3 could be 0, 1, or 2. So first I'm going to show you a bad way to do this. Okay, so this is the first way. But doing it this way would probably make you very sad. This is a bad way of doing this. This would be to say, well, let's see, the probability that R is less than 3, right? Less than 3. Well, that's going to be equal to the probability that R equals 0 plus the probability that R equals 1 plus the probability that R equals 2. And we'd have to figure all those out and add all those up, which we did. So I could plug this in and say, well, we figured this out, 0.858734027 plus 0.13279399215 plus 0.008214057. And that's going to be equal to 0.999742042. Okay, I put a whole bunch of decimals on here, decimal places, and I need to mention something at this point. So if you were to look in the back of the book, here's what the book would say. The book would say 0.999. Well, where the book gets its answers is from the table, and the table has 3 significant digits. So the book is going to use that table, and its answers will be 3 significant digits. Now, the book is not going to round to 1. It's not going to round to 1 because that means that it has to happen, right? The book's not going to say the probability is 1. So what the book will do is it's going to truncate this answer to just 0.999. So one thing to keep in mind when you look in the back of the book, they're using the table. So their answers are going to vary a little bit. So we don't want to round this to 1. We just don't want to, because then it makes it look like it has to. What happens if you have a probability of 1? Probability of 1 means that event will happen, right? So we don't want to do that. So I usually just use, extra digits like this. The book will just truncate the answer like this with that kind of an understanding. But later on, we may get, sometimes you'll get something like, let's say you have your answer. I'm just going to make this up. Let's say you get an answer like 0.543. You look in the back of the book, they get 0.541. That's going to happen sometimes. Because if you're rounding here, but you have many more significant digits from the calculator, well, they're only going to have 3 all the time, so they're going to get what's called round-off errors. So if you get this answer and you look in the back of the book and they have this answer, you're fine. You're most likely doing it just fine. You're doing it correctly. You just have more significant digits than the book. So just kind of keep that in mind when you'll see that happen sometimes. Okay, so we looked at this way. This is a bad way to do this because this requires 3 separate calculations and we have to add them all up, right, when it says less than 3. So here's another way to do this, and this way will make you very happy. So this way what we're going to do is we're going to use binomial CDF. Okay, so I'll say probability that R is less than 3. Well, we're not going to use binomial PDF this time. We're going to use binomial CDF. Binomial CDF. So, the NPR is still the same. N is 5. P, probability of success, 0.03. R, number of successes. Well, now it takes on a little bit different meaning. But here's what this means. When you have the CDF, it's a cumulative distribution. And it starts at 0. So I'm going to write this down so we can see this is cumulative. It's a cumulative distribution. So really it's a cumulative probability distribution function. But they just write CDF. So cumulative, but the key is, what we have to know is cumulative starts at 0 every time, ends at this, meaning whatever you put. I'm not gonna say ends at this. I'm just gonna say in this case ends at 2, and the key is including 2. Okay, so when you use binomial CDF, it's going to start at 0. It's going to do R equals 0, R equals 1, R equals until it sees this number 2, and it's a cumulative. It's going to add them all up. So it's going to start at 0, go to 2, and add them all together. Remember, it's going to include this one. So binomial CDF. This was actually one of the first probability distribution functions that Texas Instruments put together in their calculator. So it actually has kind of a weakness here. It's the only one that insists on starting at 0, which causes us some problems later, which we'll see right here for 3 or more. Every other probability distribution function that's cumulative in that calculator, we can tell it where to start. In fact, some of the newer calculators, not the 84s, but the ones after that, Inspire, I think, with a binomial CDF, allow you to start wherever you want to. But for us, if we're using the TI-83 or 84, it's kind of a weakness of this distribution function that none of the other ones in the calculator have, just this one, and that it always starts at 0. We can only tell it where to end. We can't tell it where to start. It's starting at 0 every time. It's ending here wherever we put it. So in all the other types of functions, there's another input where we can tell it where to start, but not this one. So when you use binomial CDF, it's going to start at R equals 0, and it's going to go up to and including this one and adds them all together. So binomial CDF should get us right to the answer right here. So I showed the calculator video before when I showed the binomial PDF. The binomial CDF is right next to it. If you go to second vars to get to the distribution and go right next to binomial PDF, and you'll see binomial CDF. So go ahead and punch this in, and you should get this same number right here. Okay, so you punch that in, and we should get equals 0.999,742,0042. Okay, so hopefully that worked. So binomial CDF is really nice when we're trying to figure out the probability of something less than. So there's like less than 3, less than 4, less than 2, something like that. Then we can go right to binomial CDF. And we can always use CDF if it says less than, because 0 is less than that. So we'll start at 0. So here's where it gets a little trickier. And it's only trickier when we have this particular cumulative distribution function. All the rest of them, it's not trickier at all. It's only because this one starts at insists on starting at 0 that makes this tricky. So this one says, what is the probability that three or more of the DVD players are defective? Okay, so three or more. First, let's just think about something, what we just looked at before. We found the probability that less than three are defective, and it's almost 100%, right? It's really close to 1, because you'd have to be really unlucky to pick 5 of them and not have less than 3 of them defective. So that's what we're going to figure out now. What's the probability that 3 or more are defective? Now this is probably going to be a really tiny number, right? 3 or more, probably going to be really small, because it's not very likely that if you pick 5 of them from that pile, and that pile has 3% of them bad, you'd have to be a super unlucky person to in your pile of 5 to get 3 or more defective. But here's what we have to think about. Okay, I'm going to first show you again the sad way to do this problem. Very sad. The sad way is to say the probability that 3 or more means R is greater than or equal to 3, right? 3 or more. Think about what that means, 3 or more. 3, 4, or 5, right? Because we're only picking 5 of them, so there can only be a maximum of 5 defective ones. Well, that means we could find the probability that R equals 3. We'd have to add it to the probability that R equals 4, and then add that to the probability that R equals 5. So we have to go through and find all these probabilities and add them all up. Okay, and we could do that. It's just a lot of work. And especially if this is more complicated. You know, what if we're going to pick 17 of these? We want to know the probability of 3 or more. You know, we don't want to go through, and this is a long, drawn-out way of doing this. So what we want to do is do it a quicker way. So the easiest way to see this, let me write this out first. Okay, now this is the easiest way, but it's going to seem a little tricky at first. So if we wanted to find the probability that R is greater than or equal to 3, well, couldn't we instead just find the probability that R is less than or equal to 2 and subtract that from 1? In other words, could we just say, let's do this instead. This is called the complement rule, which saves a lot of time in this chapter because of this, I guess you kind of call it a defect of this command, the binomial CDF command. So this may not make sense yet, but when I draw this picture here, I think it will. So what I have here is a probability distribution table for our situation. So this is R, the number of successes, and this is the probability of R. We found these first 3 out. We found the probability of getting no defective DVDs, right? Or DVD players, and then the probability of finding 1 and 2. And if we kept going, if we kept using the binomial PDF, and the same thing, just picking R equals 3, 4, and 5 would get these numbers. So this is a really tiny probability, which makes sense because if you pick 5 DVD players out of that pile, think of them, thousands of them being there, 3% of them are bad, only 3%. You pick 5 of them and they're all bad, you'd have to be like the unluckiest person around, right? So that's a low probability. So with this, it's easier to see the complement rule because I'm going to ask you some questions about this. If I add up all these probabilities, what do I have to get? I have to get 1, right? Because isn't this everything that could happen? In this experiment, I'm going to pick 5 DVD players. I'm counting the number that are defective. It has to be 0, 1, 2, 3, 4, 5, right? It has to be that. So if I add up all these probabilities, it has to be 1, right? So we know that. Okay, so keeping that in mind, we know that if we add those up, we're going to get 1. So then the question is asking us, what is the probability that 3 or more are defective? So it really wants this. This is the probability that 3 or more are defective. Well, let's say we figure this part out. Let's say we figure this. Actually, I don't want to emphasize that these are different. Okay. So we've got these here and then these here. This is the probability that r is less than or equal to 2. Okay, here's where this is going to make sense. I know all of these added together are going to be 1. So the probability that r is less than or equal to 2 is just these added together. Probability that r is greater than or equal to 3 are these added together. So if I add this to this, in other words, I'm going to make a huge equation here. This plus this has to equal 1. Has to equal 1, right? The probability that r is less than or equal to 2 is basically these 3 numbers added up. The probability that r is greater than or equal to 3 is these 3 numbers added up. But here's the thing, with our calculator, we can find these 3 super easy. We can use binomial CDF. With our calculator, we cannot find these 3 easy. The difference is these 3 start with 0. Binomial CDF insists on starting at 0. So we could use binomial CDF to find this in one step, right? Like we just did above, went from 0 to 2. Binomial CDF doesn't let us start at 3. So we can't find this directly, but if we want this and we can find this, here's an equation. Solve this equation for this thing. Well, can't I just subtract this from each side? I think in algebra you would have went, well, okay, I'm going to subtract this from each side of the equation. I'm going to subtract it from this side of the equation. That goes away, and I get the probability that r is greater than or equal to 3 is 1 minus the probability that r is less than or equal to 2. And this is this complement rule. So when we're asked to find the probability that r is greater than or equal to a number, we can't use binomial CDF directly, so we find everything else. In other words, we want 3, 4, 5. We can't find it. We can't find 3, 4, 5 because binomial CDF doesn't know how to start at 3. It only starts on 0. So instead of finding 3, 4, 5, we'll find all the rest. We'll find 0, 1, 2, which is all the rest of them, right? And subtract it from 1. And we can find this one because binomial CDF does know how to start from 0. So to use this technique, the complement rule, we would go 1 minus binomial CDF, and then we have our NPR, right? 5.032. And you can enter this all in one command on your calculator. You can go 1 minus, and then go second vars to get here. Or what some people do is they just do this first, then go 1 minus that answer. But either way you go, we're going to get a really tiny number, and we need to talk about how to deal with that number. So go ahead and punch this on your calculator however you want to, and when you check back, so if you do this in 2 steps, you'll get this 1 minus 0.99974200042, which is what we just got. And that will give you on your calculator, it's going to say 2.579958E minus 4. So this is calculator notation, which we really want to avoid. This is understood if you use an American calculator, And let's even show you where this came from. This E came from the 1970s electronic calculators. Some of you, I don't even know if you recognize this, but it used to be when calculators came out, maybe in the probably mid to late 70s, you could make them say anything as long as you could form it in this shape. So I don't know if you guys have even seen this. I'm sure some of you have. But in those days, there's no way you're going to be able to use scientific notation on a calculator, right? Like times 10 to the, and then use a superscript, -4. It's just not going to work. So what they did is they said, well, we can make an E here, right? So if you, these were electronics, so you wouldn't turn on that or that, and there's an E, and then they'd make a -4. So what this means is exponent. Exponent meaning times 10 to the -4. So modern calculators don't need to do this, but they still do for whatever, or at least a lot of them do. So we don't want to use this. This is not universally understood. Scientific notation is, right? So here's something you could do. You could write 2.579958 times 10 to the -4. This is understood throughout the world. This is scientific notation. So we could do this. This is okay, but this is bad. Let's not use American calculator notation. But what's even better for us is probably just to, do what either this or this says and move this decimal point 4 times to the left. So move it 4 times, you get 1. And then 3 more times to give us zeros. So it'd probably be better for us is just to write 0.000258 or, round it at some point. So either of these are okay. This is probably better. But let's not use American calculator notation. Now remember in the book what they're going to do here? They're going to write 0.000. So that just means with the book using the table, that's the most significant digits they can get. So they're not going to write 0, they'll write 0.000. So just kind of be aware of that when you look in the back of the book. Okay, I just want to just look at something to make sure we're clear of how this works. So if you have binomial CDF, remember cumulative is going to start at 0, go up to and include this number, whatever it is. So this is the same as doing binomial PDF twice and adding them together, right? This CDF is the same as these two PDFs added together, right? Binomial CDF always starts at 0, goes to whatever this is, which is 1 in this case. So that's the same as binomial PDF at 0 plus binomial PDF at 1, right? This means R equals 0. This means R equals 1. And this means it's a cumulative from R equals 0 to R equals 1, including 1. Okay, so just wanted to make sure we're clear on that one. Another one just to look at. The probability of at least 1. This was actually mentioned in chapter 4. I said this would be coming up. Probability of at least 1. There's a lot of work to find this because at least 1 means R could be 1 or 2 or 3 or 4 or 5 or as high as it goes. It just can't be 0. So probability of at least 1 is the same as 1 minus the probability of none. Because think about what this means. At least 1 means R equals 1, 2, 3, extending to however many there could be. The only thing missing is R equals 0. And so this is how you'll see it when it's not written out in English, when somebody doesn't say, what's the probability of at least 1 success? If they say, what's the probability that R is greater than or equal to 1? This means the same thing, right? Greater than or equal to 1. Think about what that means. R equals 1 or 2 or 3 or however many there are, right? All the way up to n trials. The only thing it's missing is this one, r equals 0. So figuring this out takes binomial PDF for r equals 1, binomial PDF for r equals 2, binomial PDF for r equals 3, binomial PDF for r equals all the rest of them. That's a lot of work, but you could instead go 1 minus binomial PDF for r equals 0. So this is the complement rule, which we only need because binomial CDF is not coded well. It should allow us to pick our starting point, but it doesn't. So because of that, we have this situation here, which we'll never see in any other chapters because the cumulative distribution functions, the other one's not binomial, but the other ones allow us to pick a starting point. We just have this because this insists on starting at 0. So as an example, let's see, let me move this up a little. Let's say we've got the probability that r is greater than or equal to 3. Well, you know what, let me not do that one. Let's change that one. Let's say r is greater than or equal to 5. Okay, so that means probability that r equals 5 plus probability that r equals 6 plus probability that r equals 7, and so on and so forth, right? However many n, it would go all the way to n. Well, wouldn't it be easier just to go 1 minus the probability that r is less than or equal to 4? Right? Because this greater than or equal to 5 means 5, 6, 7, 8, 9, 10. But what is missing is 0 through 4. If we can do this with binomial CDF and just go 1 minus binomial CDF. All right? So when we do examples, it'll make more sense. If it's not quite clicking yet, it'll make more sense with an example, but I just want to show you one little variation that we have to be careful about. What I mention all the time in math class is that details really matter in math. And the better you are at noticing little details, the better you'll be at math. So this one says the probability that r is greater than 5. Well, greater than 5 means 5 doesn't count, right? Greater than or equal to 5 means we're starting at 5, but strictly greater than 5 means we're not starting at 5, we're starting at 6. And then we would just keep on going, right? Add all these up to however many there are, to whatever n is. It's a lot of work, but it'd be much easier just to go 1 minus the probability that r is less than or equal to what? Less than or equal to what? This starts at 6, so we'd want to go up to 5, right? So the thing I'm getting you to look for is this greater than. When it's greater than or equal to or greater than, we need to use the 1 minus. If it's less than, we don't. So when you see these greater than or equal to, greater than or equal to, greater than, all of those we need the complement rule. If it's less than, we don't. Okay, so if this is like the easy problem, probably that r is less than 4. Less than 4, no problem. Because less than means we can start at 0, because less than 4 means r could be 0, 1, 2, or 3. Again, be careful. It says less than 4, right? Not less than or equal to 4. Well, as long as we're starting at 0, we're good to go. We only have to worry about this 1 minus stuff when it's greater than. Less than means we can just go ahead and use our binomial CDF, right? This is binomial CDF, NPR. In this case, we would put 3. Since these, I'm just totally making these problems up, so we don't know what N or P are, but if it's less than or equal to 4, we're good to go. That's what binomial CDF is for, because it starts at 0, goes to up, In this case, going to 3, not 4, because it's less than 4. If this said less than or equal to 4, if it said less than or equal to 4, then there'd be a 4 here and a 4 here. But the main thing I want you to see is when it's greater than or equal to, we need the 1 minus binomial CDF. When it's just less than, we're good to go with binomial CDF. Okay, I've got one last example before we try one or two of them from the book. And hopefully this will put all the pieces together. So we're going to take some free throw shots, 8 of them. We're going to take 8 free throw shots. And let's just say the probability that we make a shot is 0.7. So let's say we make 70% of our free throws, and we're going to take 8 baskets. So we're going to take a shot 8 times. We make 70% of our shots, and we want to figure out what's the probability that we make exactly 5. Now, first thing to note is equal sign. When there's an equal sign, it's always going to be a binomial PDF. Equal sign is always a PDF. When it's one of these inequalities, it's always going to be binomial CDF. If there's any kind of less than or any kind of greater than, with or without the equal part, these are all going to be binomial CDF. So for the first one, probably that R equals 5. This one is just going to be binomial PDF. Remember that equal sign is always PDF. Binomial PDF, NPR. N is the number of trials, which is 8. NPR. P is the probability of success, 0.7. R is the number of successes, 5. So if you punch this in your calculator, it looks like we have about a 25% chance of doing that. So if this question were in the homework and you look in the back of the book, it's going to say 0.254, right? So when there's an equal sign, it's binomial PDF every time. Okay, so less than or equal to 5. Okay, well, when it's a less than or equal to, these kind, we're all set to go, right? We have binomial CDF for these. Less than or equal to means that we're going to start at 0, right? Because think about this. R is less than or equal to 5. That means R could be 0, 1, 2, 3, 4, or 5. As long as you're starting at 0, we're all set with binomial CDF. As long as you're starting at 0, binomial CDF is good to go. So we've got binomial CDF, NPR, right? So it's a CDF, so we have to plug that in and see what we get. Okay, so hopefully that's what you got. And then the difference between these two is this is less than or equal to 5, so R could be 5. This is just less than 5. So in this case, R could be 0, 1, 2, 3, or 4, but not 5, right? Strictly less than 5. So because it starts at 0, we can use binomial CDF. 8.7 and 4. And if this is the last command you hit on your calculator, you can hit second enter, and this will come up again, and then you can scroll up and change that to a 4. And when you do that, then it looks like you should get 0.1941043.5. So let's just think of these and see if they make sense. So the person is a 70% shooter, taking 8 free throws. So about a 25% chance to make 5 of them. This person making less than or equal to 5. About a 45% chance. Making less than 5, looks like about a 19% chance. So, yeah, I don't know. I guess nothing seems crazy so far. Remember that every answer we get needs to be between 0 and 1. And then here is where I'm going to put this in red. This is going to get more work here. When it says greater than or equal to 5 or greater than 5, we can't use binomial CDF directly because this means r equals 5, 6, 7, or 8. Well, binomial CDF can't start at 5. And this one, strictly greater than 5 means r equals 6, 7, or 8. Okay, same thing. Binomial CDF can't start at 5 and go to 8. It can't start at 6 and go to 8. So we basically can't find this directly, so we do it indirectly. Whenever it's a greater than or equal to, we go 1 minus. So instead of this greater than or equal to 5, what we'll do is go 1 minus the probability that r is less than or equal to. We'll get all the rest of them. This is 5 to 8, we'll go 0 to 4. So we'll go less than or equal to 4. Now in this case, this is 6, 7, and 8. We'll get all the rest of those. So we'll go 1 minus the probability that r is less than or equal to 5. So hopefully this is kind of starting to make sense here. Equals is always PDF. Any of these inequalities, less than or equals, or greater than or equal to, any combination of these are all CDF. And if it's less than or equal to or less than, it's just directly binomial CDF. But when it's any kind of greater than, we need to go 1 minus, right? Because binomial CDF cannot start here. It's got to start at 0. So we find all the rest of them. So then this one we would go 1 minus binomial CDF. And we're doing 1 minus binomial CDF. And this is going up to 4. So we would go NPR. This other one would go 1 minus binomial CDF. Now this time, because they want the probability that r is strictly greater than 5, means the probability that r is 6, 7, or 8, which we can't find. So we're going to find all the rest of them, 0 to 5. We're going to find 0 to 5, right here. So that's going to be 8.75, because this will give us 0 to 5, right? Binomial CDF starts at 0, goes to 5. This starts at 0, goes to 4. So one thing that does happen, it's kind of an easy mistake to make. When you have these, don't forget about the 1 minus. It's easy just to do this. But normally if you do that, if you think about your answer, it won't make sense. So just be careful. Make sure you go 1 minus this and then 1 minus this. So try it and see what you get. So hopefully you'll get these numbers. This is basically saying the probability that this person makes 5 or more shots is pretty good, right? 81%. 81% chance that this person who makes 70% of their free throws is going to make 5 or more. And this is basically saying greater than 5, which means 6 or more. 6 or more, there's about a 55% chance. And then finally, this last one, make at least 1. Well, remember, this is kind of a key, at least 1, which I'll just say the equivalent of that is greater than or equal to 1. But we don't ever want to find at least 1. We're going to have to go 1 minus the probability of none, right? So whenever you see that at least 1, this means r equals 1 or r equals 2 or 3 or 4 or 5. Think how much of a pain this would be if you had to do this individually. You go like, okay, at least 1. R equals 1, 2, 3, 4, 5, 6, 7, 8. Right? Again, that's what this means too, at least 1. you'd have to figure all those out. Well, instead of that, the only thing missing is 0. So let's just figure out the probability of making none, subtract that from 1. So this one would just be 1 minus binomial. It's the equal sign. Equal sign means PDF. NPR. Now in this case, sometimes students accidentally put CDF and they say, hey, I got the same thing with a CDF. Well, you will only for 0, because binomial CDF is cumulative, but there's nothing to add up yet. It's just 0, right? So it's good just to get in the practice of whenever you see an equal sign, it's a PDF, right? Equal sign, PDF. But in this one particular case, when it equals 0 and you put a CDF, you'll get the same thing. So what do you think the probability that this person makes at least one shot is? They make 70% of their free throws. They're taking 8 free throws. Isn't this going to be pretty high? Wouldn't it be really unusual for this person to not even make one shot? So the probability they make at least one is probably going to be a pretty big number. I mean, it's going to be close to 1, I would guess. So if we punch this in, then we will get, well, if you look in the back of the book for a question like this, they're going to say equals 0.999. The calculator puts a few more decimal places, so the calculator says 0.999, and then there's a 93439. So hopefully this problem right here will make sense. Equal sign is PDF, less than or equal to or less than is CDF, greater than or equal to or greater than is 1 minus CDF. And then we will try one or two of them in the book here, and then you guys should be good to go to try them yourself. So let's try this number 16. I think between what we've done so far, I think if we do number 16, you guys should be all set. So number 16 in this section of homework says, Richard has just been giving a 10-question multiple choice quiz in his history class. Each question has 5 answers, of which only 1 is correct. You guys are not going to believe this about what it says next. It says, since Richard has not attended class recently, he doesn't know any of the answers. Assuming that Richard guesses on all 10 questions, find the indicated probabilities. Oh, Richard. Okay, part A. What is the probability he will answer all questions correctly? Well, first, let's just write down some things. It's a 10-question multiple choice quiz, so n equals 10, right? N equals 10. It's a 10-question. Each question has 5 answers, of which only 1 is correct. So if he's guessing, the probability of guessing correctly is 1 out of 5, right? Or for the decimal fans, it's 0.2, right? 1 divided by 5 is 0.2. And just to make sure everybody's still on top of things, if P equals 0.2, what does that imply about Q? If P is 0.2, what's Q? 0.8, right? P is the probability of success. If this person guesses, they've got a 20% chance of being successful on each question, which means they've got an 80% chance of being unsuccessful, right? P is probability of success, Q is probability of failure. Again, we're just counting success as the things that we're looking for. So if we're going to count the number of correct answers he gets, there's a 20% chance of that happening for each question. So part A says, what is the probability that he will answer all questions correctly? In other words, what's the probability that R equals 10? Well, do you think that's very likely? He doesn't know any of the answers. He's going to guess at all of them. What's the probability that he gets all 10 correct? Got to be pretty slim, right? If he gets them all correct, I'm going to ask him for the winning lottery tickets. Ticket numbers. So is it binomial PDF or CDF? What's an equal sign? So it's PDF, right? The question is, what is the probability he will answer all questions correctly, all 10? So binomial PDF, it's always NPR. And from here we punch it in the calculator, and we're going to get a really small number. My calculator says something like 1.024 times 10 to the negative 7. So if I write this as a decimal, let's see, this decimal point is going to move 7 times to the left, because the negative means to the left, right? It's getting smaller. So move it 7 times to the left, which means to move it once and then 6 more times. So I'm going to have 6 zeros. 1, 2, 3, 4, 5, 6. And then you have the 1, 0, 2, 4. So it's pretty small chance of that happening. Even though it's a small chance of happening, it doesn't mean students like Richard won't try it. Because they do. Okay, you guys won't be able to relate to this guy though. So part B, what is the probability that he will answer all questions incorrectly? In other words, what's the probability that R equals 0? Well, this still isn't going to be all that likely, right? Because let's think of it, I think it's easy to relate to as a basketball again. Let's say somebody makes 20% of their shots. Not very many, right? 20%, that's pretty low, but they're going to take 10 shots. So they'll probably make 1 or 2, right, out of 10 shots. 20% of 10 is 2. So you'd think maybe they're going to make a couple of them. So we're going to figure out the probability that they still make none. So B, what is the probability that he will answer all questions incorrectly? So he gets really unlucky, gets them all wrong. So that's going to be binomial PDF, N, P, but this time R is 0. So let's try this one and see what we get. Okay, so when I did this, I got roughly 0.107. I'll just round it there, 0.107. So about 11% chance, right? About 11% chance that he would get none of them right. So it means he's probably not going to get none of them right. He'll probably get a couple of them right, or, you know, a small number of them correct, just from randomness. So part C, let's see what this says. Part C says, what is the probability that he will answer at least one of the questions correctly? Compute this probability 2 ways. First, use a rule for mutually exclusive events and the probabilities shown in table 3. We don't need to do that. That's basically saying do it the long way, which we've done that. I showed you the long way in the lecture a little earlier. So we'll just do this the way that pretty much everybody would do it. So the probability he will answer at least one correctly. At least one means R is greater than or equal to 1, right? Doesn't this mean at least one? He's going to get at least one right. So it's probably pretty likely to get at least one right just from guessing, right? So the problem is this is a greater than, so we can't use binomial CDF because at least one, just think about what that means. That means R equals 1, 2, 3, all the way to 10, right? The only thing it's missing is 0. So at least 1 equals 1 minus none, right? So this is 1 minus the probability that R equals 0, right? That's the only thing missing. The only thing missing here is a 0. We know if we add up all these together, we have to get 1, right? These are all the outcomes, 0 through 10. If we add them all up, all those probabilities, we have to get 1. So this is getting all of them except for this one. So we can just subtract it from 1. And we can say this is equal to 1 minus binomial PDF, because it's equals NPR. And you might even notice we just did this one up here. It's 0.107. So basically it's going to be 1 minus 0.107. And 1 minus 0.107 is 0.893. So it's about a 89% chance that this person's going to get at least one right. Right? So hopefully you're okay with this idea now of when it's greater than a number, means we can't start at 0, so we can't use binomial CDF, so we go 1 minus all the rest. And at least 1, the easier way is 1 minus none. Okay, then there's one more part here, part D, which says, what is the probability that Richard will answer at least half correctly? Well, at least half? Well, there's 10 of them, right? 10 of them, so at least half would be 5 of them. So what's the probability that R is greater than or equal to 5? Greater than or equal to 5. Well, again, we've got this greater than part, which is a problem, right? 5, 6, 7, 8, 9, or 10. Well, we can't use binomial CDF here because it won't let us start at 5. So we're going to find all the rest and subtract it from 1, right? So what we can do instead is go, well, this is equal to 1 minus the probability that R is less than or equal to 4, because that less than or equal to 4 gets all the rest of these. We want 5 through 10, which we can't find directly, so we find it indirectly by finding 0 through 4 and subtracting that from 1. Because remember, these are all the outcomes possible, 0 to 10. We want 5 through 10, which we can't find, but we can find 0 through 4 from binomial CDF. So let's find 0 through 4 and subtract it from 1. That'll be equivalent to this, right? Just to make a quick vertical table this time, but this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And we could find these probabilities here for each of these by using binomial PDF for each one of these. And what we want is 5 or more. We want all of these. We want the probability that R is greater than or equal to 5. Well, we can't find it directly, but we can find all of these. And we know that if I take the first one and add it to the second one, I have to get 1, right? Add up all those, I have to get 1. So we're just going to find these and subtract it from 1. Okay, so what we're going to do is go 1 minus binomial CDF NPR. Remember, CDF, start at 0, go up to and including 4, which gets all of these. You go 1 minus that. And when you do that, this by itself is about, let's see. Well, if you go 1 minus, what I got was roughly 0.033, right around there. So I got like 0.03279. So I'm just rounding here. So remember, don't forget the 1 minus. If you do this one first, you can go 1 minus and go second answer on your calculator to get that. So you can do this all in one step or do them separate, but you should get 0.033. And with that, it's kind of a long lecture video, but I think you should be okay now for the homework. So give it a try. Some of them may be a little tricky, so be persistent, stick with it, be stubborn, keep working, and send me any questions you have. And I'll talk to you guys soon.